I'm Siti Makhsin from the University of Manchester. Thank you, Dr. Patricia and the committee of IEEE conference for choosing and giving me this opportunity to present a part of my ongoing project. Today, I would like to present about surface modification of titanium-coated glass substrates embedded with acrylate-based hydrogel film for optical metal leaky waveguide biosensor. First of all, as an introduction, I just would like to recall about what is biosensor is all about. It's about a device that consisting a biological recognition system or bioreceptor and also the transducer. So the transducer can be from optical and the rest of that we discussed for a few days before. And particularly today, I would like to talk about the optical transducers, whereby I use optical biosensor, and I use a few of these properties in order to generate the signal for my sensor. To be more specific, my sensor is hydrogen-based metal leaky waveguide biosensor. It's actually a 4-layer of the device that consisting a high refractive index material as a glass substrate. We do have a metal layer here, it's about 9.5 nanometer, just enough to have a Fresnel refraction here. And we do have a waveguide layer here that made from the hydrogen matrix, as well as we do have a cover layer for the system to flow the water later. So we use LED light as a light source and also CCD camera to monitor the results, the outcome. So for example, there is any changes in terms of refractive index inside the hydrogen matrix. It will change the resonant angle from position 1 to 2. Therefore, we can see the changes here that we can develop the result based on that. Um, for my project, I use acrylate-based hydrogels, and why I use it to improve the sensor sensitivity, because particularly my project is about to detect the bacteria. So therefore, we required acrylate hydrogel matrix as a waveguide sensing layer. For the first is because of the porosity or the nature of the acrylate-based hydrogel is about have a 3D network, whereby it's allow the samples to diffuse in and reach at the strongest position whereby the detection happen. So therefore, it can enhance or boost the signal. The second one is about biocompatibility, and also acrylate-based is synthetic origins. So the quality from one batch to another, we can control it properly. Because in our previous work, we use like natural-based hydrogels such as agarose and also chitosan. So we can't control the quality very well. From one batch to another, we receive a different quality on that. Therefore, we move to synthetic origins, as well as we can easily control the surface functionalization that we want to introduce into the hydrogel structure for the immobilization of the protein later. So we also can control the concentration of that, how much we want to load to the surface for the recognition species, as well as this 4-layer of structure with the waveguide using a hydrogel layer actually can increase the depth of penetration compared to the conventional structure. Therefore, it's very suitable for the larger detection, of the larger analytes such as a bacteria in more sensible range. Okay, so this is a criteria that for perfect biosensor. Oh, sorry. But today, I just focus on the stability, whereby it's very important so that when we test the sensor is not giving any failure and is stable during the detection. So in order to study about that, because this is our previous results that we optimize the composition of the hydrogel from acrylate-based polymer, and we get very good results, and also we require a very good porosity for the structure. So this is one test when we're using the optical sensor, we can have the porosity testing using that one. So whereby we use glycerol as a small molecules example, and BSA as a protein, which is shown the large size of the molecules. So we set the refractive index of this buffer at the same value. So if there is a change that happen at the same sensitivity happen at the same layer on the waveguide layer, it will cause the same change in the peak angle here. So it indicates for us that the porosity is good enough whereby we allow the analyte to diffuse in at the same point. But however, the problem occurs when we try to prolong the detection more than 1.5 hours because we try to immobilize is the protein for the bacteria. However, we found that the hydrogen easily to detach from the substrates. So there is one solution which is we call silanization process, whereby it's a process to cover the glass or the substrates with the organofunctional group so that it can provide the covalent bonding between the substrates and also the hydrogel. So the ideas come when we want to try a few type of the chemicals that commonly used for this process, and because it can provide the SiO-Si group here, same with this too. However, we also want to introduce the acrylate PEG NHS during the surface treatment because we thought that this NH group can bind with this NH, so it provides another covalent bonding. And the PEG 2000 here is also can improve the hydrophilicity of the substrates. So it can, because my hydrogel is about 60% of water, so it's require very hydrophilic surface. So this is the method that I use to prepare my chip until how I do the detection. So for the pre-preparation step, this is the common step, but we're adding one step here at the end, whereby we treated the TI-coated substrate with these three sequence. And after that, the fresh sample, we deposit the hydrogel using the spin coating process, and we cured the gel using the UV lamp. And this is the common the probe that we use to get the signal. If you can see from here, this is where the chip we clamp it, and we have the water bath to control the temperature effect so that we can minimize the effect of the temperature. Sorry. So we put the flow cell whereby this is the sample to in and this is the sample to go out. And we use a prism coupling to couple the light in and out. So for results and discussion, for the first sequence, which is using TMS PMA as chemicals to treat the substrates, as you can see, I'm not sure is it clear or not, but the hydrogel just form like a small dots throughout the surface without any proper homogeneous layer. So it indicates that the surface become very hydrophobic. And sorry. Actually, this is because TMS PMA consists 3 methoxy group, whereas it made this substrate become very hydrophobic. So it's not suitable for my case. So we moved to uptase and acrylate PEG NHS, so I got some result with that. So with a substrate that treated with the uptase, APTES, we can get some signal here, yes. However, if you monitor at the column 3 and 4, this is using a baseline water, then this is using a 1% glass raw. Sorry. And this is when at the end of detection, we remove all the glass raw and flow back with water. If you can see at column C3 and C4, the peak just about decrease, and it indicate that it just the hydrogen just detached from the substrates. So meaning that it's not fully covered the surface using the uptase, and that's maybe because of only some of the binding like electrostatic charge just happen on the substrates without any strong binding. But however, in terms of response time, if you can see here, we compared this result with the previous one that we optimized before. We do have some improvement in terms of sensitivity. Yes, it's good. However, in terms of the homogeneity of the layer still not certified. So we move with sequence updates and also treated with acrylate PGNHS. So we varied the spin speed as well during the spin coating process. However, at high spin speed above 6,000, the waveguide that form here is quite thick and broad, and therefore it's not sensitive enough. And below than 6,000 at 5,500, the waveguide that form is It's very thin, and this is like about the thickness is just about the below the cut-off point. So we use the profile from 5,500 RPM for further detection of different refractive index buffer. If you can see here, I just want to highlight from baseline with water. You see this is the peak, but at the end of detection, after we change a few buffers here, at the end we flush away with water, we can see it remain at the same position. So this is what we monitor on the CCD camera. So meaning that the binding is so good, and the hydrogel is like fits very well on the substrates, and it do the job. And in terms of real-time monitoring, so this is the response time when we convert to the change in the P angle. So each of the buffers change good, and shown the diffusion time is very short. And when the interesting part of this, when we compare our system with the previous reported in agarose-based methyl leaky waveguide sensor, our improvement is about 45% from the previous one. So this is made due to the porosity of the acrylate-based hydrogel, as well as the functional group from NH that covalently bond with the NH group from the acrylate. Therefore, it gives very high sensitive on the device. So in order to study about the stability, so we prove to the protein interaction. So in here is a BSA and anti-BSA immobilization on the hydrogel. So we do have one control channel here, and this is the test channel. So this is we keep with PBS so that it can we can monitor as a references, and this is where we change from water. Then we move to PBS and PBS with BSA, and then we wash away the remaining BSA that not bind with the hydrogel. Then we flew the anti-BSA, and if you see that there is a changes here that when we wash away with water, so that if there is any binding, it will not shift to original position, but it just stick here. So this is the amount that we can convert to study how many how much the anti-base A can bind with the BSA. So this is still ongoing project whereby after this we need to immobilize the secondary antibody on the top of the anti-BSA with the bacteria. So yes, above 3 hours, the signal is strong, and this is proof that by having a surface modification, even in the in the substrate itself, can also influence the sensitivity and also the stability of our device. So, as are my conclusions, okay, we have successfully optimized the procedure to treat the substrates using these chemical updates, but need to follow by acrylate PJNHS because our gel is from acrylate-based polymer. And spin speed also influence the properties of the waveguide signal. So we need to get the desired thickness for the good signal for the waveguide. And we improve the sensitivity about 45% and the stability about more than 3 hours. So with that, I would like to acknowledge and thanks to my supervisor, Dr. Patricia Scully, and my co-supervisor from the University of Manchester, as well as all the technical support from University of Manchester, as well as my funded from Ministry of Higher Education Malaysia. Thank you.